You know that feeling, right? You're in a loud bar, you hold up your phone, and somehow it just knows the song that's playing. Or maybe you've uploaded a photo to find similar ones online. It feels like total magic, but it's actually some seriously clever computer science. So let's pull back the curtain and figure out how computers search for things that, well, don't have any words. All right, so first things first. To really appreciate just how cool the solution is, we have to understand the sheer scale of the problem. And honestly, it's huge. The simple truth is, we're all living on top of this massive, and I mean massive, ever-growing mountain of digital media.
I mean, just think about it. Every single photo you take, every video you upload, it all adds to the pile. And as you can see from this chart, the amount of this data is just exploding. Now, here's the kicker. Unlike a text document, all this stuff is what we call unstructured. And that makes finding anything specific a huge challenge.
So that leads us right to the big question, doesn't it? I mean, a computer can search for the word cat in a document in a split second. That's easy. But how does it search for the idea of a cat in a photo? Or the melody of a song in an audio file? How do you search for something that has no words?
Well, the reason this is so incredibly hard actually has a name in computer science. It's the core challenge we really need to wrap our heads around. It's called the semantic gap. And this diagram just lays it out perfectly. Up at the top, you've got the raw signal, the literal pixels in a photo or the sound waves in a song. That's all a computer sees. But down at the bottom, that's what we get, the knowledge, the meaning, the actual semantic part. And that giant chasm between the two? Yep, that's the semantic gap.
So here's the bottom line. The entire mission, the whole point of multimedia search, is to build a bridge across that gap. It's all about teaching a machine how to look at that raw data and figure out what it actually means to a human.
Okay, so how in the world do we build that bridge? Let's start with images. How do engineers actually go about teaching a computer to see, to go from just a bunch of colors and pixels to, understanding what's actually in the picture? Well, the simplest first step is an idea called query by example. It's pretty much what it sounds like. You give the computer an image and you say, hey, find me more pictures that look like this one. Super intuitive, right? But it's got some pretty big problems. Oh yeah, and this slide illustrates the problem perfectly. Let's say a system is just matching basic stuff, like color. You search for a red, white, and blue American flag stamp. Sure, you might get other flag stamps, but you're just as likely to get a picture of a skier or a rock that just happens to have the same color palette. The system isn't seeing a flag, it's just seeing colors. It's missing the meaning. So these early methods, they were looking at what are called global features. Basically, they were analyzing the color and texture patterns of the entire image all at once. And look, it kind of works for finding generally similar patterns, like you see here, but it almost always misses the specific subject of the photo. Clearly, a smarter approach was needed, so people started asking, okay, instead of looking at the whole picture, what if we could teach the computer to find and focus on just the most interesting parts of an image? And that thinking leads us to the real hero of our image search story, something called salient points. Think of these as super distinctive spots in an image, like sharp corners or unique edges that are incredibly stable. It doesn't matter if the lighting changes or if you zoom in or even look at it from a different angle, these points stay recognizable. So here's how it works. Step 1. The algorithm scans the image and flags every single potential point of interest. And as you can see, it's a lot. It's basically a whole cloud of possibilities. But then, and this is where it gets really clever, it filters out all the junk and keeps only the truly salient points, the ones that are the most stable and the most distinctive. What it's actually doing is creating this unique, simplified model of the object. It's like a fingerprint for the image. And the result of this whole technique? It is a massive leap forward. Because now, by matching these unique fingerprints, instead of just broad colors, the system can give you these highly accurate search results that actually understand what's in the picture, whether it's seagulls, some graffiti, or the Golden Gate Bridge. All right, so that's basically how computers learn to see. Now, let's switch gears and see how a very similar idea works for audio. How do we teach a computer to hear? And for this, we've got to talk about the most famous example out there, Shazam. So let's go right back to that noisy bar we were talking about. You've got people talking, glasses clinking, all that background noise, and yet your phone somehow picks out just the song and tells you what it is in seconds. How on earth does it do that? Well, the secret is remarkably similar to what we just saw with images. It's all about fingerprinting. And this slide shows you exactly why it works so well. On the left, you've got the audio fingerprint of a nice clean song. On the right, that same song has all kinds of noise mixed in. But look, even though some of the little details are different, that core constellation of the most intense sound peaks, it's still there. It's a super robust signature. And the process itself is actually pretty straightforward. First, the system creates a visual map of the sound. That's called a spectrogram. Then it zeroes in on the loudest peaks across different frequencies. After that, it maps out the constellation of those peaks to create that robust fingerprint we talked about. And the final step, it just matches that fingerprint against a massive database of songs. That's it. That's the magic behind Shazam.
Okay, so we've seen the clever fingerprinting tricks for both images and audio. Now let's zoom out a little bit and look at the bigger system, the whole machine that puts these pieces together to make a search actually work.
This diagram here shows the general blueprint. And really, it doesn't matter if it's a song, a photo, or a video. The basic flow is always the same. First, the system extracts those key features, right? The salient points or the audio peaks. Then, it organizes them in a super efficient way. That's called indexing, so it can search through them lightning fast. And finally, it finds a match for your query and shows you the results.
So, to quickly sum it all up, we started with this huge problem, an absolute explosion of digital media. The main hurdle to overcome was that semantic gap between what a computer sees and what we understand. The brilliant solution was to create these robust, unique fingerprints for images and sounds. And the result? It's the powerful search technology that we all just kind of take for granted and use every single day. You know, when you peel back all the layers of complex technology, it really comes down to something very simple. The whole goal is just to find stuff, images, video, sound, that you, the user, are actually interested in, and then rank it so the most relevant results pop up right at the top. Which leaves us with a pretty fascinating thought to end on. We've gone from searching simple text to searching images to searching sounds. As computers get even better at bridging that semantic gap, at understanding meaning, what's the next frontier? What's the next unsearchable thing they're going to help us find?